So welcome to this talk. I'm presenting this paper that has been presented at IPDPS last year, in fact, at 2017. So this is joint work with my ex-postdoc, Sabela, who has actually done pretty much all of the work. So I'm really presenting her work here, so that should be put in context. But unfortunately, she's not able to present this work because she's now working at Google and doesn't have the time to do this simply. So let me go ahead with this. One of the things that I would like to first emphasize is that what we've been observing in the last years, really the last 15 to 20 years of computing, is an incredible increase in complexity in microarchitectures, and very precisely memory microarchitectures. So if we go back to the first CPUs, the actual von Neumann model, that's kind of the original envisioned model, in the sense that we have a very simple CPU, a very simple level 1 cache, and then some kind of DDR memory that holds code and data at the same time, right? This is the original model. There's one of those guys, right? Then this quickly was extended to dual socket systems, where we have two CPUs with two separate level 1 caches and a simple single DDR main memory. Then this was extended to multi-core CPUs, where we now suddenly introduce a shared level 2 cache. So we have now two separate level 1 caches, but then a shared low-level cache that both of them access, that are again connected to one DDR memory. And when I say one DDR memory, we may even be talking about multiple banks here, right? I'm ignoring the multi-bankness of modern systems. Then this was extended to, of course, well, let's combine these multi-core CPUs into multi-socket multi-core CPUs. So you see that this gets more and more complicated in the sense that we now have these CPU cores. They all have private level 1 caches as usual. Then some of them have shared level 2 caches. Some of these shared level 2 caches are actually connected to other level 2 caches in the communication system. So this is your on-chip communication, or specialized communication like QPI or one of these, or hypertransport in AMD. And the on-chip communication is, of course, in this gray area. And then you're connected to another dual-core system with this shared cache structure. And then you definitely have multiple, or in most cases, you have multiple banks connected to these systems through multiple memory controllers. So this link is kind of a memory controller. And then the latest incarnation of these systems is something like that, where you have a truly distributed memory system, in the sense that you have multiple cores with private multi-level cache hierarchies that are then connected to some kind of global bus-like system. It doesn't have to be a bus, but some global network that is then itself connected to multiple memory controllers. And somehow you have to figure out how to work with this. So this is here, most of you are probably recognizing this, the architecture of the Xeon Phi KNC node, which is one of the more complex architectures. And in fact, today I'm going to talk about the architecture of the KNL node, which is a follow-up of KNC, which is even more complex than this because it's not a single ring, but it's a set of rings, so the ring of rings. So in the sense, the architecture that we want to discuss today is kind of at the pinnacle of memory complexity, I would say. So it has 3 different memory models, 5 configuration modes, and just for booting the system, I have to decide for 1 out of 15 different configurations. So as far as I understand, this enormous complexity has not been here today. But how do we typically go if we want to optimize codes for these systems? Because after all, we are interested in high-performance computing. So we try to really use these systems as efficiently as possible. So I give you a chip, and your goal is to make it as efficient as possible. So there is, in fact, an engineering discipline about this. It's called performance engineering. And I'll let you to read the description that is kind of an official description of the field of performance engineering. This is much of what we do, in fact. It's an engineering discipline so far. And the idea of this engineering discipline is really that you manually provide codes and you manually tune them to a given architecture. So what do you typically do when you do this? Well, you need to be familiar with all these things, non-uniform memory access. You need to understand the topology, the bandwidths in this topology that I just explained to you a little bit with these very simple case studies, or increasingly complex case studies, in fact. You need to understand caches, you need to understand the microarchitecture, you need to understand many, many different effects of that system in order to achieve the highest performance, in order to tune your code to that particular architecture. Right? And of course, you have a wonderful engineer that is typically exemplified as a code ninja who can take your code, like let's say you're a climate scientist, you can take your code and scramble it, turn it around, transpose it 15 times, and then magically it is going to be a fast code in that target architecture. And of course, we all know how to trust engineers, because we all know that about, well, 50% of the engineers are versed in the median. Right? And then things like this happen, so you may have some engineering disasters. So at the end, it's really how good your engineer is, right? It is kind of a discipline that is partially an art because it very much depends on the quality or on the strength of the people you involve, and very much an engineering discipline because, of course, there are some general rules how to do this. But the question is, how do we get to these general rules? In getting to these rules, I would like to introduce my vision, or the vision of the lab here, really that is going into the direction of scientific performance engineering. So here what we try to do is we try to really understand the underlying scientific principles that performance engineering should be based on. So rather than relying on the expertise of individuals that have learned how architectures work, that have learned how various heuristics in their career, how to optimize for certain things, I would like to put this on a more rigorous basis on the scientific method. But how does the scientific method work? Well, typically what you do is you observe your system, right? So you think physics, you make experiments, and from that experiment, you derive a model. You derive some kind of hypothesis that you then later test. And that hypothesis and the testing helps you to understand the system at a different level, typically at a more mathematically abstract level as the cobbling that was suggested at the beginning, what the typical performance engineer does. And then once you have understood it, we have observed it, you have measured it, you have modeled it. So this is really an abstraction step. That abstraction step enables you the understanding, and you can use that understanding to construct a new system that is then on a much more rigorous basis. Because you can often, if you do this right, you can prove that your new system in this understanding is actually optimal or close to optimal, of course, under the assumption that your model is good, right? And models are always an approximation to reality, but that is at least something that we can apply some rigor to. So let me now explain how I would envision this process to work with the memory subsystem optimization on the Xeon Phi KNL node, right? So let's first explain you a little bit more how a KNL node actually works, actually looks like. So KNL node, as I mentioned, is a ring of rings. That's a very complex thing, so let's just imagine it as a 2D mesh. Okay, that's a simplification. Again, I'm making some model simplifications here at the very beginning. And it has a rather complex memory subsystem because it has these two DDR controllers, so to be precise, GDDR controllers that have this integrated memory controller here and here. So these are two tiles in this overall chip architecture, so this is the chip. And then it has multiple EDC controllers that are connected to MCDRAM. That's a different kind of DRAM. It's a faster DRAM. It is better connected. It's basically just better connected, and it's an unpackaged DRAM, right? So the links are also not that long. And then each of these tiles that we can see here consists of two cores, one to the left, one to the right, with a vector processing unit, a 1 megabyte level 2 cache. So each of these cores, of course, has a level 1 cache, a rather small one. They have a shared level 2 cache. And then they have a so-called cache home agent, and that is the major point of discussion in the following. These are the black things here. These are the cache home agents, because that is these elements control the data movement on the chip. Okay, and I'm going to explain you how they control the data movement in a minute. So let's first discuss one of these modes. I explained at the beginning there are 15 different modes we can boot that architecture into, or that chip. One of them is called the all-to-all mode. So let's just stick with the all-to-all mode for now. The idea is that at some point, some core, as you know, issues a load or store instruction. Okay, so just a normal x86 instruction says like load that address, let's say, okay? So that load is going to be, of course, first forwarded to the cache, and if the cache, let's assume there's a cache miss, so the cache does not have that load, otherwise it'll just serve it and it's fine. So there's a cache miss, then it's contacting the cache home agent, the local cache home agent, to figure out, well, where is that where is that memory address? So where do I need to load it from? Do I need to go here, 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 or one of these many memory controllers? So the way the architecture does that is it hashes the address. So it applies a to us unknown hash function to the address. And that hash function, as a result, gives you one of these other cache home agents in the system. Let's just say that there, okay? So, and then this cache home agent, so you route your request to that cache home agent through the network on chip. It's a very simple network on chip. It's a Cartesian network, so you always route first along the x dimension and then along the y dimension, right? Very simple. And you get to your owning cache home agent. So the owning cache home agent then knows, by definition, it has to know, where that particular cache line that houses that particular memory address that I have accessed, right, is. So that tells you, okay, this thing here figures out, okay, it's now in this MCDRAM controller, right? So it's somewhere in this physical MCDRAM over here. So what does it do? Well, it routes again, first in the X direction, then in the Y direction, or you can transpose it if you want, to that particular MCDRAM. And then, of course, now I still need the value in this, this tile. So that MCDRAM, cache home agent here again, sends it back to that tile, right? This is how a single cache miss works on that architecture. Okay? So there's quite a bit that happens, as you can see. It's much more than what happens in a normal architecture. So, okay, this is now a little bit concerning if you're an architect, right? So you have 72 of these tiles, there are many of them, and basically all your cache misses fly through the whole chip. Right? So this can, well, you could argue it may not be the best idea because it's a 2D chip after all. So what you could do to improve the situation is, or what Intel specifically did, is they introduced two modes. Now we are getting into these more specific modes. This was the all-to-all mode, where the chip is considered a flat architecture. And here we have two more modes. One is called quadrant mode, that cuts the chip into 4 quadrants. And the other one is called hemisphere mode, that cuts the chip into 2 halves. The quadrant mode is the encouraged mode to be used. The hemisphere mode is more of an experimental mode that is not really encouraged to be used. So let's talk about the quadrant mode here. So what you do here is basically that you ensure, it's a similar mode, but when you boot the architecture in that mode, you ensure that the cache home agent that owns a certain memory address, right, or a certain cache line, in fact, not a memory address, is in the same quadrant as where this cache line actually resides. Right? Okay, so it's rather simple. Let's say this guy again requests something that is up here, but now the hashing is adjusted in a way, actually not the hashing, but the placing in the memories is adjusted in a way that the cache home agent, as I just said, is in the right quadrant. Right? So again, I'm routing again to that quadrant, of course, to that cache home agent, which is now in the correct quadrant, so it's going to be locally routed, locally inside the quadrant, right, to that correct MCDRAM, and then that returns it. So that you can already see there is some form of locality, right? Because the second request is not moving very far, right? It's not moving from down here to up here, but it's kind of in the same quadrant. Okay, so this is the quadrant or hemisphere mode, and again, emphasizing on the quadrant mode. There is one even stronger mode that you can boot your architecture into, because if the architecture or the chip would tell you where the data resides, then you could place, I mean, the operating system could place the thread on a core that is in the right quadrant, right? Because in the previous mode, this core that requests is still in the wrong quadrant, right? So now we could just say, well, this is called the subNUMA clustering 4 or 2 mode, and again, we prefer the 4 mode. And the idea here is that through the NUMA extensions in the Linux operating system, you can figure out your placement of the memory and your placement of the threads, or the operating system does it for you, but you can control it through the operating system. And now you make sure that if you request something, that memory and your core placement is in the correct quadrant, right? Okay, so we do the same thing. We still have that tile responsible, but now we have the right position for that requesting thread. We again do the XY routing, do the XY routing to the MCDRAM and back, and you can see we're covering less of the chip space, right? So this is an optimization. Okay, cool. So now we have already understood pretty much all of the configurations for this particular architecture. Now you may say, well, why is this not the obvious best one, right? So, well, that's a discussion. But after all, you can boot that chip into all these different architectures. But the question that you're now wondering about, or I would be wondering about, well, does this all matter? Is this important? So what's the real access cost, and what's the real cost for cache versus memory? What are the numbers? Right? So, and this is where much of Sabela's work came in. So Sabela understood the architecture of the chip in great detail, and also understood the cache coherence protocol. So this is an abstraction of the cache coherence protocol. It's the MISI protocol, actually from Wikipedia. The actual chip runs the MISIF protocol, so it has another state that's a forwarding state, but that's of minor importance. If you know the MISI protocol, and I'm somewhat assuming that you know it here, these 4 states, the one is modified, exclusive, shared, and invalid, and various transitions between these protocol states. And again, remember, each cache line in the system is in one of those states. Right? And this is how any shared memory system, or most of the shared memory systems today actually work. It's not quite any, but about 95%. And depending on the state, the system will issue different operations to the various memory subsystems. So either other caches, right? In the sense, for example, if it's shared, then I know that there is some other cache with high likelihood that has that value. If it's exclusive, I know that there is no other cache and I need to get it from main memory, and similar if it's modified. If it's invalid, I also know that I don't have it at least, right? So it's not clear if somebody else in the system has it. But I'm somewhat assuming you know the rough idea of this cache coherence protocol. So what we did in this work is we took this knowledge of all these cache states and we measured the various configurations of that system just to understand, again, how to parameterize a model that we could later use to optimize that system. So we have these multiple modes, as I discussed. So we have the software NUMA mode, which is really this SNC2 and SNC4 and SNC2, right, that I described a couple of minutes ago. Then we have the software uniform memory access mode. So this is where the software is aware that the chip is actually not uniform. Here, this is where the software is not aware that the chip is not uniform. Okay? And here we have the quadrant, hemisphere, and all-to-all modes. Right? So I discussed all the modes in the last 2 slides. So and then if we just look at the cache-to-cache transfer, and these are times in nanoseconds determined by a benchmark called Benchit from the Technical University of Dresden that we modified to have better statistics. And here you can look at the cache access time. So for example, if your cache line is a level 1 cache locally, then it takes about 4 nanoseconds to access it. A couple of cycles, so good, no problem. If your cache line is in SNC4 mode and is in modified state, right, in the level 2 cache, then it already takes 34 nanoseconds to access that line, which is much more than the 17 or the 14. And that basically means that if it's modified and I'm reading it, I need to write it back as well, right, as mandated by the protocol. So there's some write back overhead. And we can argue about this, but this is an implementation detail that we believe is the case. So again, this is all speculation. We are not quite sure because Intel doesn't tell us exactly how the protocol works, because that's obviously their IP. And now we can see, well, that's your local overhead, and then the remote overhead. As soon as I'm fetching a cache line from a different tile, then it gets very expensive, right? So you have 107 to 122 nanoseconds, depending on the different states of the cache line. And we can also see, and this was a very interesting result, that the location, so basically, if I'm requesting the cache line from a direct neighbor on the chip, or if I'm requesting from the cache line from somewhere very far away on the chip, right, from another core or cache that's very far away on the chip, makes only a 15% difference. That was very curious to figure out. We don't know why. Right? So I would have expected a much higher difference between the locality. Okay, so what we also see is a bandwidth, not too exciting, and then we have the copy bandwidth as well. And another very interesting effect we found is that there is absolutely no congestion that we could provoke on that chip, which means the benchmark we ran is about half the cores fetch cache lines from the other half of the cores, and we try to observe that they fight with each other for the resources on the chip, because after all, the bisection width of a 2D torus is very low. It's linear, right? Linear versus quadratic. Somehow, that has no impact on that particular chip. It's also a very curious observation that I could explain now, but I would have to break an RS NDA, so I cannot explain it. Okay, at least not here. Okay, so then we also looked at contention, but again, all these numbers, let's move a little bit faster. So the other thing we looked at, so this is cache-to-cache transfers that I just talked about. But now, what if the cache line is in main memory? Right? So that's the memory-to-cache transfer. Again, we have a very similar set of experiments. So we looked at the software NUMA mode, the software UMA mode, and basically the same configurations that we have before. There are now 2 different modes how you can look at your memory, because I explained at the beginning that you have 2 different memories, right? You have the DDR memory, the GDDR memory, and you have the MCDRAM memory. The MCDRAM is on-package, very fast memory, and the GDDR memory is somewhat normal DDR, right? No, graphics DDR. So it's also fast, but not very fast. And we will actually see what fast means. And I should correct myself. It's actually not fast versus very fast. It's lower bandwidth versus high bandwidth. Because for some definition of fast, the MCDRAM is slower than the normal DRAM. So there is now a flat mode and a cache mode. And what does that mean? So somehow the programmer needs to know in which of the 2 memory classes, DRAM or MCDRAM, a particular data value resides. Right? So if I'm creating an array A, how do I know that it's in MCDRAM or in DRAM? Well, by default, I don't know. but then we have the flat mode and the cache mode. So in the flat mode, I can determine where to place it. In the cache mode, the high bandwidth memory is essentially used as a fully associative cache in front of the lower bandwidth memory. Okay? So in the cache mode, essentially everything is somehow cached in this much smaller, or I shall say the MCDRAM, the high bandwidth memory, is much smaller than the large, slower memory, lower bandwidth. While in this first mode, I can explicitly control it. Okay? So, and this is where we can now have a differentiation between DRAM and MCDRAM here. And now if we look at the latency of these two types of memories, so DRAM, again, is the low bandwidth memory, but we can see it has quite a low latency as well. So in fact, it's low bandwidth, low latency. And the other one is high bandwidth, high latency. So that's a little bit interesting, at least, because it's the first time that I have seen a memory, at least in practical computer systems, that is not just has higher bandwidth, but also higher latency. Typically, it has higher bandwidth and lower latency, like the cache. Right? Better in both parameters. So there may be some tapes that have that feature, but typically it's this way. Okay, and then we can look at all these other numbers, but let's skip for now. But what I want to focus on is that the bandwidth is in fact much higher, 4 to 6 times higher of this high bandwidth memory, obviously, because it's high bandwidth memory. And the other interesting observation on that system is we really need read and write operations. Actually, we need them in a ratio of 2 to 1 in order to achieve the spec'd bandwidth of the chip. So if we have a ratio of 1 to 1 read to write, then we will not achieve the spec'd bandwidth. It is really optimized for having 2 write operations, 2 read operations for every write operation on that chip. It's also curious. It's also one of the only widespread architectures I've seen that has this feature. So then if you look at the cache mode, where we now really cannot distinguish between DRAM and MCDRAM, because it's really just, the MCDRAM is just a cache for the DRAM, right? But we see that the cache mode by itself is now 20% slower than the DRAM used exclusively. So that would suggest that you may actually slow down applications, and we will see this later, latency-bound applications. And of course, the bandwidth suffers a bit, but it's still higher than the DRAM, right, the GDDR. Okay, very good. But now, imagine you're this performance engineer. I've now given you a 10-minute spiel about these very numerous numbers, right? And now I tell you, okay, you need to figure out all these modes and take into consideration all these numbers, and you now need to design the best code and the best mode on that particular architecture, right? And you will probably say, okay, can I quit, right? So that's obviously a very daunting task to keep all this in your head, and this is generally not a good approach. So we have generated these numbers to understand the system, and now what we're going to do with these numbers, we're going to abstract them into an abstract model that we can actually use for performance engineering or for scientific performance engineering. Otherwise, this would be a useless exercise. Of course, this exercise is useful in itself to really understand details about the system, right? So that I don't want to dismiss. But in order to make it useful for programmers, you need to abstract this. So what we did is a very simple experiment, or started with the simplest possible. So let's say we want to design a communication-only algorithm. And that algorithm is the simplest algorithm you can imagine. It's the broadcast algorithm. So basically, I have one data item in one cache, and want to make sure that after the operation, all the caches, all the cores have that data item in their cache. Right? I want to do this as fast as possible. It's a very relevant operation for many, many computations. Actually, most of them. I mean, reduction is similarly important, but we will get to this. And it's relatively nice to explain in the sense that every broadcast algorithm can be, okay, every work-optimal broadcast algorithm can be described as a tree. Okay? So now we just say, well, we design a tree that we call a multi-array tree. And this tree has multiple levels, of course, like any tree has multiple levels. And at the different levels, or we call it depth here. Okay, fine, let's call it depth. And at the different levels, we have different number of children. So here, for example, at the first level, I have 2 children. At the second level, I have 3 children at each vertex. Right? So this is a flexible tree, so to say. So now the question is, what is the optimal configuration for that tree? So what is the optimal number of levels? If I say, you want to reach all 72 cores on the chip, how do I determine the optimal number of levels and the optimal number of children per level? Right? Well, I can do this because I can now take these numbers that I had before and write them down in this very simple, a little bit frightening looking equation, but these RRs is really a remote cache miss, RLs is a local cache miss. So basically you plug these numbers into this equation, right? So it's not that hard. And you can really just compute the overall tree cost. The sum here determines the tree depth. And then this this Ki is really the level size. And you can make this a minimization problem because overall what you want to do is you want to minimize the time over all possible number of levels and children per level of this overall equation under the constraint down here that you reach the number of threads that you want to reach, right? So, okay, relatively simple. So you just solve this equation essentially, and that gives you the best D and Ki. So that gives you the optimal tree in that model. Okay, so you say, fine. But first of all, I would say, well, the typical performance engineer would not do this, right, today. That's not the state of the art what you do. Today, what you would do is you would open some papers and you would say, oh, well, some people think a binary tree is a good idea. Some other people think a binomial tree is a good idea. So let's implement binary and binomial trees, right? That's the typical cobbling approach that I mentioned at the very beginning, right? So there's some state of the art and you just repeat the state of the art. This will pretty much always either have you an ingenious idea, right? So you have to have a new kind of tree idea, or, well, you implement one of these existing heuristics, right? However, if you solve this optimization problem, we are basically taking away this you need an ingenious idea out of the process, right? We just say, well, you don't need an ingenious idea. You just phrase this whole problem as an optimization problem. You solve this optimization problem, and then mechanically, like somebody who really doesn't understand and doesn't need to understand anything about the details of the system, you get this optimal tree cost. In fact, this is how the tree looks like for the 72, the optimal tree under the constraints I mentioned before for the 72 node case, 72 cache case. And who would come up with that tree? I mean, it's kind of weird if you think, right? So the first level has a very large number of children. The second level has only 4 children. So, okay, I wouldn't exactly know why that is the best solution, but that's what the optimization algorithm says. However, once you have this, once you understand your tree shape, it's very easy to implement. Right? Because, well, sure, it's basically just another tree. But getting to that tree is the hard piece. But we just took the hardness out of the hard piece by making it a mathematical optimization problem. Right? And this is very small, so this is easy to solve because its n is 72. Right? So in fact, we solved this with exhaustive search on that particular chip because the chip is constant size. For larger problems, that is harder because we all know that ILPs are not that easy to solve. And in fact, that's not even an ILP. Okay, but now let's say how this performs in practice. So in practice, this performs rather well. So we have 2 different modes of distributing the threads, but let's just focus on one. So one is blocking, packing, and one is scattering the threads, but one is, looking at one is okay. So, and this is really what we achieve with Intel's MPI here, the blue ones. So these are box plots, and again, this is the median is the line, and then we have the 25th and 75th percentile in the box plots and the standard deviation as usual. And the black ones down here with a much lower variance are the optimal trees that we designed. So we ran the optimization problem for various numbers of threads up to 64 here. Actually, there should be a 72 as well. Okay, so in this case, it's 64. And we achieve, on average, a 13 times faster performance and a much lower variance compared to Intel MPI. So there's a small cheat here because Intel MPI is a distributed memory implementation of MPI. We use a shared memory implementation. So we have some benefit. So you may argue, okay, that just comes from the difference in the memory domains. That is not the case, because we achieve a similar speed up over the barrier function. So we applied a very similar strategy to optimizing the barrier function itself, which is not a tree. It's a dissemination algorithm, but you can use the same optimization, very similar optimization formulation. And we are 7 times faster than Intel's highly tuned OpenMP. With that, I want to remind you that the Intel Xeon Phi KNL is actually a multi-billion-dollar investment from Intel, right? So that's a large, just a tape out in the engineering of that architecture is a large cost, which means they have all incentives to highly tune their OpenMP environment, and that is their standard environment for that architecture for multi-threaded programming. So, and we achieve easily, within a couple of days, basically, after we have established that model, a speed up of 7x over this. And you can look at the details over here. We also achieve a speed up of 5x for the reduction algorithm on that architecture, which is an OpenMP reduce of various sizes. I think these are all small sizes here because we talk about latency. Okay, So now we have shown some success with that model in a very small setting, right? Basically only kind of communication, group communication algorithms. Let's look at a little bit more complex architectural question, and that is sorting. So how do we sort? Because now we know how to do this, so let's do big data because it's a very hip topic today, as you know. Okay, so let's look at the bandwidth distribution. So here we run Stream Triad, a very well-known benchmark, again on that system, to understand whether we want to run the sorting on all cores or on some of the cores. So here on the x-axis we have the number of threads as a first parameter and then the number of cores as a second parameter. So we can, for example, use on that system 256 threads on 64 cores. So that system has 4 hardware threads on each particular core, and we see the achieved gigabyte per second. So we already see that with 32 cores, we somehow achieve the maximum bandwidth we can get on that system. Okay, it's a very simple experiment. However, if we now look at, and this is the cache mode here, right? Okay, very important. If we now look at the flat mode where we can control MCDRAM versus DRAM, we see that in fact, if we run all threads on all cores, we achieve a significantly higher peak bandwidth than the, in MCDRAM. In DRAM, it's not such a big difference than running with smaller numbers of threads. So somehow, if we assume that sorting is a memory bandwidth limited problem, which it's often described at, right? Then we would see, okay, that is we should basically run with all cores in flat mode in MCDRAM if possible, right? If the problem fits in MCDRAM. So this is the simple engineer's conclusion. But let's now apply the modeling again, and we're big fans of sorting networks in the lab. So we look at a bitonic sorting network here, which is basically a fixed structure where we run the same operations over and over again in a loop over the data, and at the end turns out to be sorted, right? So you can read all the theory about this. This is, in fact, also one of the fastest sorting mechanisms if it's an in-cache operation. It may be improved for out-of-cache. So this is not necessarily the best sorting algorithm for that particular architecture, but is one that has been shown to be competitive. So we can actually model the sorting, and I don't want to get into too many details here, but we can write this all down. Basically for a level 1 access, so if my data fits into level, or the share of the data fits into level 1, share of the data fits into level 2, and the remainder of the data somehow sits in main memory, right? So we can easily model this, and of course we have the different access costs here at the various stages, but I don't want to go into too much detail. You can look at the paper if you're really interested in this. And let's get to the numbers actually. So here we have 1 to 256 threads. We sort 1 kilobyte size integers in that particular system. And we have various models here. We have first the measured points. These are the black dots that go up here. And then we have one model that just considers the memory latency. The red one, not so great. We have one model that just considers the memory bandwidth. The green one, not so great, right? And then we have another model that's called the full model, either for latency or for bandwidth, but we see both of them perform pretty well here, that contain also the synchronization overhead. And as you can imagine, if you sort 1 kilobyte integers on 256 threads, there's quite some synchronization overhead, right? Because there are rather small chunks for each thread at the end. So we can see that this full model actually models it pretty precisely. So we have to say that this is a little bit outside the pure memory modeling strategy that I discussed at the beginning, but it's very easy to add the synchronization model to this, and you can see the equations in the paper. So this is basically what I just discussed. And interestingly, what we can now do with this modeling, well, we cannot just predict the performance pretty accurately, but we can also give you a good number of threads that you shall not exceed in order to sort 1 kilobyte of integers. So we can basically tell you with this sorting algorithm, it doesn't make much sense to run with more than 3 threads, right? Because the synchronization overhead is going to dominate your execution performance. And this is a very nice model in the sense that we can actually really tell you what is useful to be done in a very practical scenario. It's like the average parallelism in the work depth model, but very much in practice, right? So, and if you actually look at the equations, it is nearly equivalent to the average parallelism in the work depth model. So you can actually back this up with some solid theory. So now let's go a little bit larger. If we do the same sorting algorithm of with 4 megabyte, the same number of threads here, and we see the curve somehow move to the right. And it's getting more interesting because the measurements, first the latency, I mean, this is the overall sorting time really here, right? The latency of the sort operation goes down and then up again, right? Because obviously parallelism helps, right? But also the synchronization of the parallelism hurts you at some point if you don't have enough data. So pretty clear to everybody who has a basic understanding of parallel computing. And again, the models capture it at various granularities. So you can see that the effect of the parallelism helping is well covered by the two memory models, latency and bandwidth. But the synchronization is not covered because it's just not modeled, right? So it's pretty clear. And if you combine the two models, you actually model both effects reasonably well. And now what you're, okay, so I should have waited for this. And again, the parallelization boundary now moves to 5. So you can use 5 threads reasonably. And how do I define reasonable? Well, I define reasonable in the sense that we don't spend more than 25% of the CPU resources on non-VARC, like synchronization, or something like this. But we can adjust this number, right? So reasonable is really up for your definition. For very large data, 1 gigabyte in this case, it's pretty obvious that you want to use the whole chip because it's a very large data, right? So synchronization costs pretty much play no role, and then the memory model is just great, right? So we can actually safely ignore synchronization in that particular scenario, so no problem here. And we should always use all the cores in that particular model. So now let me get to the end of this talk, and the most surprising result, at least for me, with this one particular algorithm on this one architecture is that, well, I didn't answer the question, right? And this was, if you've watched the marketing of this architecture, it's really, this is a breakthrough in memory bandwidth, like this MCDRAM, wonderful new technology, 500 gigabyte per second. Okay, it's already a year old, so today it would be a terabyte per second. But nobody was really talking about the slightly higher latency. And what we found in the model, as well as the practical measurements, is that the higher bandwidth of the MCDRAM is not really a good indicator of performance of at least sorting. Because sorting is not strongly, but partially latency bound, because it has this log square depth. I mean, if you want to talk in terms of arc depth, has a log square depth of the sorting network itself. And that, of course, depends on the latency, right? So you have some penalty that you get from the slightly higher latency that is just about eradicating the benefit you get from the faster bandwidth. It's a very interesting observation, and this actually is scale invariant. So even the large data suffers from the log square depth latency penalty on that architecture. So this particular sorting, and again, this may not be the best sorting for KNL, this is just one sorting algorithm we looked at, is not really faster. Right? And there are many other that have made similar observations for other algorithms in that particular case. So this really means that we need to design new algorithms if we want to use this MCDRAM more effectively that are more latency tolerant than at least the simple sorting networks. So the question is if this is possible. And of course, the algorithm design space is rather flexible. So we can actually design sorting algorithms that are latency tolerant and maybe not sorting networks, but other things if we wanted to. So with that, I would like to close my presentation, and I'm open for questions and discussions. So thank you very much, and